Can you see the text? Maybe I have to better to enlarge it a little bit. So let's start with this very simple exercise in which you see that there is an actor composed of 3 nodes, and the first one is the source of the packet, and then there is a destination. In this case it's a host. The nodes are connected by 3 links, and you have the parameters of the links reported above. So the first link has a capacity of 128 kilobits per second and a propagation delay of 1 millisecond. Capacity is refers to the speed of the transmitter that is connected to R1. In this case, we are only considering one direction, so from R1 to A, and so we are only interested into the interfaces of the transmitters that are located at the interfaces of the 3 nodes towards the next node. We have 2 packets that are transmitted by A, and the question is what is the time that at which the 2 packets will arrive, transmitted by R1, and the question is what is the time that will take to the 2 packets to arrive to A. And so we have to consider all the possible delays that can occur to these packets when they are propagating from R1 to A through the intermediate nodes. All the nodes here, since there is no other specification, they are assumed to work on the store and forward mode. So they receive the packet and then they transmit it. In order to study this problem, we have to use the graph that we showed last time, which is called the time diagram. And here, first of all, we can see what are the data of the problem. So we have the length of the packet, which is 512 bits. Okay. We have the propagation delays and the capacities. So if you remember from the lectures, once you have the capacity and the length of the packet, you can immediately calculate the transmission time of the packets at each interface. Okay. So in the generic interface TI, in the generic interface I, the submission time is given by the length of the packet, which remains the same from the source to the destination, divided by the speed of the output, the transmitter interface. Okay, this is the general formula. And in this case, the calculations are very simple, because if you take, for example, T3, which is the speed on the last link, the transmission time on the last link. Here you have C3 divided by, L divided by C3. And here you have 112 bit divided by, 512 bit divided by 512 kilobit per second. Kilobit per second means 1000 bit per second. So at the denominator I have 512,000. So it means that the result will be in milliseconds if we don't consider these zeros. Okay. And this is 1 millisecond. Then you have transmission time 2. You see that the capacity of the second link is half of the capacity of the third link. And this means that the transmission time will be twice as much, okay? So it's 2 milliseconds. And on the first link, the capacity is still half the second, so the transmission time will be the double, 4 milliseconds. Okay? Now we have to build the time diagram. We have 3 interfaces, so we need 3 different time axes. And then we can start drawing the packets. Okay. So the distance between the lines doesn't matter. You can choose it as you want. The important is that you select a time unit which is the same for all the axes, and in this case very convenient that I choose one small square that is corresponding to 1 millisecond. Okay. So the R1 starts sending the packets, and it will produce it one after the other. The first packet is the transmission of the first packet will take 4 milliseconds, which is T1. So we can draw it in this box. This is the first packet. Unfortunately, it's not very easy to draw this. And then after, no, this is too much. Okay, that should be 4 square. And then you have the second packet that is transmitted right after. Okay, then they are transmitted, they start propagating, and the first propagation delay is 1 millisecond. So it means that this bit, which is the last one, will arrive to R2 after 1 millisecond, and the same for all the other bits. Okay, this is R1, this is R2, this is R3. And actually, we did one more line. What happens when the packet arrives in R2? Once it has been all received, so the last bit has arrived in R2. This is the first packet. R2 will start transmitting it once again towards R3. Okay? But this time the transmission time takes only 2 milliseconds instead of 4. Okay? So the first packet is retransmitted starting from this instant, and its transmission time is shorter. When the second packet arrives at R2, the first packet has been already retransmitted completely. Okay? So the interface in R2 is free, and R2 is able to send the second packet immediately after. This is not the general case, okay? But in this case, it's like that. So the first thing that you should take care when you are drawing this kind of graph is if the packets are transmitted immediately or if they have to wait for be transmitted, because the output interface is busy transmitting other packets that arrived previously. Then the two packets propagate on the second link, and they will take 2 milliseconds to get to the to R3. Okay. Once the first packet has arrived in R3 and completely arrived in R3, R3 starts sending it on the output interface towards A, and in this case the transmission speed is twice as much as the one of the previous link, so we have already computed the transmission time, which is half, and it will take only 1 millisecond to be transmitted. The same for the second packet. Okay. Then we have the last propagation, which is the last propagation delay, which is again 1 millisecond. Okay. After this propagation delay, the packets arrive at the destination. A is not retransmitting them anymore because it's the final destination. Okay. So what we have to compute and to answer to this problem is the time that the total transfer time of the two packets in the network, and if you consider this time as time t0, is the time when R1 started sending the first packet. Then for the first packet, the time that we want to calculate is this one. Okay. It is the time between the transmission of the first bit at the first transmitter and the arrival of the last bit at the destination. For the second packet, it will be that one. Okay. So T, let's call it T1 for the first packet, is equal to the composition of all the segments that you find, that you can read on this axis. Okay? So it will be T1 plus tau1 plus T2 plus tau2 plus T3 plus tau3. Okay? This is quite simple. And the final result is 4 plus 2 plus 1 plus 1 plus 2 plus 1. It will be 11 milliseconds. So what happens instead to the second packet? We want to calculate the same also for the second packet. But you can just make a quick reasoning as in the previous case and arrive to the result. There is, however, a quite convenient graphical way to combine all the times. That is this one. Okay. So if you take the final instant, that is the arrival of the last bit to the destination, and you start moving inside the time diagram, you're able to combine all the segments in a graphical way by doing this. Each time you have a point where you are leaving an axis because you find a segment that is going to the axis above. You follow that point. Okay. Then when you arrive here, you see that you don't have immediately a segment that is going up. So you can follow the segment that you find in the horizontal direction. Then you find the segment that is going up, and you follow that segment that is going up. Okay. You write the axis representing R2. You don't have anything going up immediately, so you follow the horizontal direction. And now we are there. Then you find the next segment that is going up. And then you're moving horizontally until time t equal to 0. Okay. So now you immediately identify the components of the transfer delay, because here you have propagation delay, tau 3, then you have a transmission time t3, propagation delay tau 2, transmission time t2, propagation delay tau 1, and then 2 transmission times, okay, twice t1. So when you write it, you can start from the end. So you find tau 3 plus t3 plus tau 2 plus t2 plus tau 1 plus t1 plus t1. Okay. In this case, it's very simple. It's the same as the previous time t1 plus this extra component is t1. So since t1 is 4 milliseconds, the total sum is 15 milliseconds. Okay. Is it clear? So let's move to the second exercise, which is basically very similar to the first one, except the fact that now you can see that the capacities of the transmission channels are decreasing instead of increasing. Okay, so the first capacity is 512 kilobits per second, the second is 256, the second is 64. So in this case, things are not linear and simple as here, but you have to take into account that since the transmission times are increasing, the second packet will have to wait for the first packet to be completely transmitted at the intermediate steps. Okay. So now let me insert some space here. and let's draw the time diagram again. Okay. We have already computed well, the length of the packet is the same as in the previous exercise, 512 bits. And so we already know that T1 is equal to 1 millisecond. T2 is the double because the speed is half, 2 milliseconds. Here T3 is C3 is 64 kilobit per second, which is one-fourth of C2. So the transmission time T3 will be 4 times transmission time in the second link. So it will be 8 milliseconds. Okay. So let's draw again our graph. Propagation times are 1, 2, and 4 milliseconds, propagation delays. Let's start at this point here. Here we have the first packet, and then the second packet that is transmitted immediately after by the first interface. And then they propagate, they make the second packet a different color. So they propagate, and the first propagation delay is 1 millisecond. So you have these two lines. Then we arrive at the second interface. And in this instant, the first packet has been completely received by R2. R2 starts transmitting it, but it will take 2 milliseconds. Okay. So you can notice that the last bit of the second packet arrives in R2, while the output interface is still busy in transmitting the first packet, in retransmitting the first packet. So the second packet will experience this, in this interval of time, a queuing delay, because it will remain stored in the output queue that is located here inside R2 until the first packet has been completely transmitted. So the second packet will be sent starting from this point and for the next 2 milliseconds. Now we have the propagation. And this time it takes 2 milliseconds as a propagation delay. Okay. So the first packet arrives at this instant here, and now R3 starts retransmitting it, but this time it will take 8 milliseconds to transmit the packet, to retransmit the packet. So it will take, this is 4. Okay, all this time. Okay. When the output interface of R3 is free and is not busy anymore, R3 starts sending the second packet that was stored in the output buffer. Okay. Now I am not showing anymore the initial propagation of the first bit, because the drawing is more clear, but principle there should be another segment also here. Finally, we have the last propagation, which takes 4 milliseconds. So we start from this point, and the first packet arrives at destination in that moment. The second packet arrives at destination in this moment. Okay? This is the total transfer time of the first packet, and this is the total transfer time of the second. So T1, okay, is given by, okay, you have this is the same as before, because the first packet does not experience any queuing delay, so you have tau 1 plus T1 plus tau 2 plus T2 plus tau 3 plus T3, which is 1 plus 1 plus 2 plus 2 plus 4 plus 8 milliseconds. The total is 18. Okay. Now I want to calculate the transfer time of the second packet. Let's do the same trick as before. So we start from the end here, okay? And we move leftwards towards time t equal to 0. And here, when you are moving this axis, you find a segment going up, so you go up. Here you find a segment going straight, going horizontal, and then another segment still going horizontal. Okay. So you don't move up. Actually, in this case, there is here a segment that is going up, but you are considering the first packet now. Okay. So what is relevant for the first packet is the segment that is going up. And you cannot go any further on the left side. So we can move up. Then we find an horizontal segment, and we move horizontal, vertical segment, and finally the last horizontal segment. Okay. At this point here, if you are going up here instead of here, is exactly the same. It's just a little bit more complicated to make the calculations. So let's write down the final sum. So we have tau 3, which is this segment there. Then we have 2 times T3 3. Okay. Then you have tau 2, T2, you have tau 1, and T1. Okay. So this is 4 plus 16 plus 2 plus 2 plus 1 plus 1. This is 20, 24, 26. Okay. Questions? So let me move to another exercise. Okay, leave exercise 3, it's too long. You can go to exercise number 4. Okay. So in this case we have different topology. In particular, R1 is connected to R2, and R2 is connected to two different destinations. And the two destinations means that they are connected by two different physical links, so by two different interfaces in R2. Two interfaces are independent, the output interfaces, and also the output buffers, which will hold the packets, are different. And you have to take this into account while you are doing your analysis. And in this case, we have 4 packets that are transmitted by R2. The first 2 are going to A, the second 2 are going to B. Okay. Here we have still L equal to 512, just to make things, calculations easy. Always remember to put the unit of measurements, okay? Because you are quite old, you are graduate students, but many of your colleagues who did the exams before forget to put the unit of measurements. If you don't put unit of measurements, then the result is completely arbitrary. You have always to specify. So let's do the analysis in this case. Transmission times are the ones that we have calculated before. So T1 is 2 milliseconds. T2 will be 1 millisecond. T3 is 8 milliseconds. Okay. This is R1. This is R2. And then we have to split this graph because you have two different destinations. So now let's start considering A. Then you will have to consider B. Okay, you can do it by drawing another graph, which is clearer, or you can also do it by drawing another line here, but then you have to be careful on how you match the different packets that you are drawing. So we can start by drawing the packets. Let's assume that we are starting from here. R1 will produce the 4 packets one after the other. The first one are going to A, the second ones are going to B. Okay. Transmission time is 2 milliseconds. Propagation delay is 1 millisecond. Yeah. Okay. What happens in R2? Now we have 2 packets that are going to A and 2 packets that are going to B. The 2 packets that are going to A are retransmitted starting from this point. The speed of the output interface of R2 towards A is twice the speed of the output interface of R1. So the packets will take less time to be transmitted, and in particular they take 1 millisecond. And so the second packet does not experience any queuing delay because it is transmitted immediately when it arrives to R2. Then we have the propagation. Which takes 2 milliseconds. And the packets arrive to A. Okay. So here we don't have 3 hops, just 2 hops. What happens to the packets that are instead going to B? Now let me see if I can do a smart thing. This time we have now B. I'm not interested in these two packets anymore because they were queued in a different queue output in a queue, but I have to take care about the packets that are going to be. And the transmission speed of interface C3, which is the one that is going connected to B, is only 64 kilobits per second. So this means that transmission time is 8 milliseconds, and therefore, in this case, the second packet that is going to be will experience a delay, okay, a queuing delay. So the first packet is starting to be transmitted here at this time, 1, 2, 3, 4, 1, 2, 3, 4. It will take 8 milliseconds, and the second packet will be transmitted only after the first packet has gone. Okay. Then we have the final propagation, which is 4 milliseconds. So it means that we are going. Okay. Okay. So you have to compute all the total transfer times. Let us compute only the last one, the one of the second packet that is going to be. And so we can start from here. Then we have this segment. Then you have this whole long segment. Then we can go up, and then we have this final part. Okay. So the time that is taken by the second packet, that is going to be TB2, is composed by this is called interface number 3. So tau 3 plus, then we have 2 times T3 plus tau 2, tau 1 plus, and then you have to count 3 times T1. Okay. This is giving 4 plus 16 plus 1 plus 3 and it should be oh no, sorry, this T1 is equal to 2 milliseconds. So this is 6. It's 27. Okay. Okay, so now in the remaining time, which is not so much, but maybe you can do it, I would like you to solve this last problem by yourself. No? And let's see if you are able to solve. This is more complicated, but the principles are always the same. So you have the transmitting the source node, which is R1, and it is sending 6 packets, and there are 3 destinations, A, B, and C. The first 2 are going to A, the second are going to, the other 2 are going to B, and the final 2 are going to C. Okay? The ones that are going to A are taking 3 hops. The ones that are going to B and C are only taking 2 hops. Packet size is always 512 bits, and the interface rates are, and the propagation delays are there.